In section 3.1.3, we'll be talking about eigenspaces. Definition 3.1.3, eigenspace. Let A be an n by n matrix with eigenvalue lambda. The eigenspace of A corresponding to lambda is the set of all vectors in Rn so that AV equals lambda V. All right, this includes the zero vector. It's every single vector that works. So it's the zero vector and all eigenvectors of A with eigenvalue lambda. When the matrix A is obvious from context, we will only write E lambda. Sometimes there'll be multiple matrices, and so this will be important notation. So for any n by n matrix A and any lambda in R, the eigenspace E lambda A is a subspace of the Euclidean vector space of dimension n. All right, so this isn't especially hard to prove. We almost already have done it because E lambda is a null space and we know the null space is a vector space. I'm going to reprove it using the three properties because we also wanted for linear transformation on abstract vector spaces, and so this proof will translate well in that case, so I will not reprove it. So let's prove it now. So our proof would apply to eigenspaces in general vector space as in section 3.2. All right, I need to show that the zero vector is in this eigenspace. Well, if I multiply any matrix by 0, I get 0. And if I multiply lambda by 0, I get 0. So yes, 0 is in the eigenspace of A. Now I'm going to take two eigenvectors, two elements of E lambda A, and I want to check that V plus W is also in E lambda A. So V's in E lambda A, that tells you that A times V is lambda V. Same thing for W. If W is in E lambda A times W equals lambda W. And so if I look at what happens if I multiply A by V plus W, I would get, well, I can distribute. From linear algebra 1, we know we can distribute here. And then the first one will be lambda V, second one will be lambda W, and then I can factor. And so I get that V plus W is in E lambda A. All right, so this would apply for any linear transformation T because this is just what we assumed linearity would give us. All right, so if I take K in R and V in E lambda R, I want to check that KV is also in E lambda A. All right, so V is in E lambda A. That means that AV is lambda V. So if I look at A times KV, now K is just a number, so it factors out in front. In fact, this is one of the two properties of linear transformation. So I get AV, AV is lambda V, and then the two real numbers can get multiplied and I can switch the order. So I get lambda times KV. And so yes, KV is E and is in E lambda. And so we've proven the three properties. E lambda A is a subspace. Of Rn. Good. All right, so let me go back and show you something from this example right here. I asked you to find one eigenvector for each eigenvalue, but really you had tons of different ones. This here is the eigenspace. The eigenspace is this that we found, -2, 1s. It's the set of solution to this linear system. All right, so you have multiple ones. really, it's a subspace, and so you could start talking about a basis of the eigenspace. You could start talking about generators and all of this stuff.